So under solid state, the first concept is to understand the classification of solids. Okay. So we don't need to talk much about the basics of solid because we know it is a form of matter which is rigid, which has definite shape, definite volume, right? Molecules are not free to move. In solid, the particles cannot move, but what can they do? They can vibrate at their fixed positions. So solids can be classified into two categories. One is the crystalline, the other one is the amorphous. Can you just tell me one example of each form in the chat box? In the chat box, can you tell? So crystalline form, crystalline is structured, amorphous as irregular, correct? Correct. So crystalline solid means it has, as you said, regular ordered arrangement. Like, you know, sodium chloride, you might have known about diamond, all of these, which have a proper regular certain kind of arrangement, we call them as crystalline type of solids. Okay. And also you can tell that all the particles there or the atoms or the constituents of particular solids, they're arranged in a definite geometrical pattern in a 3D space, basically. Okay. Yeah. Good, Adyasha. So the amorphous solid means what? Whose constituent particles, they don't have any regular or any orderly arrangement. Like, you know, glass. Glass looks like a super cooled liquid. So glass doesn't have an order. If you break a glass, there's no even breakage. You know, there's plastic, someone said polymers, rubber, starch, proteins. All of them fall under the amorphous solids. They don't have any regularity. Also, maybe here and there, short range of regularity is possible, but there's no longer range of regularities, right? So let us just do write the differences slowly. So the internal arrangement of particles is regular. It is regular. That means they have definite geometry. Okay. What about the amorphous form? The internal and arrangement of particles is irregular. Means same. They do not have definite geometry. They do not have definite geometry. This is the basic thing. So we have to understand the differences deeply because in the competitive exams, you have to apply all these rules, right? And you know, they have sharper melting points, sharp melting points. Obviously, the reverse of it. They do not have sharp melting points. Okay. Third, there is regularity in the external shape. External form. When crystals are formed. There is no regularity. The external form. Please let me know once you're done copying this. Can I clear the screen?
Ma'am,
Okay, okay.
done, ma'am.
All of you done, right? So let's continue. Crystalline amorphous forms. We wrote 3 differences. The fourth one is crystalline solids. They give you a regular cut. That means, every smaller piece that you cut, it has some dimension. When you cut, crystalline solids give a regular cut when cut by knife. Amorphous. They give you irregular cut. They give you an irregular cut. Next is, they have a characteristic heat of fusion. Characteristic means everything, every specific solid has its own, heat of fusion values. That's what they mean. And they do not have characteristic. They do not have. You continue writing it. Write that. Okay, so they do not have characteristic heat of fusion for amorphous. What about it? Crystalline solids. Let me write they are. So they are rigid and their shape is not distorted by mild distorting forces. Whereas amorphous solids are not very rigid. These can be distorted. These can be distorted by any bending forces or any compressed forces they can distort. Only one more point is left after this. Can I clear the fourth point so that I'll fill that? I'm sure all of you might have completed the fourth one.
Yes.
I'm clearing that. I'm using another color for differentiation. Last one is very important. If you have a NEET, they might directly ask you which of them are anisotropic or crystalline solids are anisotropic. What does this mean? That means physical properties such as refractive index, conductivity, thermal expansion, they are all different in different directions. They are all different in different directions because of the orderly arrangement that happens because of the orderly arrangement. Different directions. This is due to the orderly arrangement of the particles. This, whatever notes I'm giving, is purely for completely for both NEET, JEE. I mean, the levels include for both level till JEE advanced. So in detail, we'll learn the same for the amorphous here. Amorphous solids. Why to write that? Sorry, amorphous. Okay, they are isotropic. This means that various physical properties are same in all directions. They are same in all directions. Why? Because of random arrangement of particles. That's all about the differences. If you are done, let me know.
Done, ma'am.
Good. So, I also amorphous substance, if you observe, they are referred as sometimes supercooled liquids. They are also called as supercooled liquids because they possess disorderly arrangement like liquids. You know that glasses and all are the examples. right? So super cool liquids is done. So what do we use? Like what are the uses of these amorphous solids? And these amorphous solids, as I said, examples are glass, different plastics and all. They are used in different things. Also, amorphous, so many uses, constructions, housewares, laboratory equipment, everything is made up of glass and plastic, right? So amorphous silica is the best material for converting. It's an interesting fact. Converting sunlight into electricity. Sunlight into electricity. That's it. That's it. I don't need to talk about the crystalline substances uses because we know diamonds uses, we know sodium chloride uses everything. Can I clear? Can I clear?
Yes, ma'am.
So we have to understand what does a crystal lattice mean. First, crystal lattice. So all crystals, crystals actually have regularly repeating atoms. That means, for example, you have a cube now like this. So to this cube, there's an again other cube which is attached. So there is a regular arrangement of same thing. It is repeating. Okay, so it has a lattice. All crystals generally have regularly repeating atoms, molecules, or ions. Okay, which are the basic units of any cell. Okay. So let me say, write the definition. Crystal lattice is also called as space lattice because these crystals and all we observe generally in the 3D arrangement. So what is the definition? Regular three-dimensional arrangement of identical points in space. Or you can also say that an array of points showing how molecules, atoms, or ions are arranged at different sites in 3D space. Also, if I can show the diagram, as I said, if I say this is a unit cell, every point here, which I will mark with blue, is called a lattice point. Okay. Very important points, understand? Each lattice point, it has the same environment or environment as that of any other point in the lattice. If you actually club, similarly this cube, draw one bottom, one beside anywhere. If you see every point will have like same number of, same environment, same kind of environment. So The constituent particles of a lattice, the constituent particles, they have always been, they are represented by a lattice point. They are represented by a lattice point. Irrespective of whether it contains a single atom or more than one atom. If you can clear, we're done talking about the space lattice. Just let me know if you're done.
Done, ma'am.
Everyone else is done, right? So you might have seen so many cubes together, na? We'll understand basic terminologies first in solid state. That is unit cell. Unit cell. This is the smallest repeating unit. As I said, in this space lattice, when repeated over and over again, results in a crystal of the given substance. As I said, see, if you have substance, if you actually have a bigger cube like this, okay, in this now, there are so many more cubes. Each of it now, so many more cubes. So this one thing is the unit cell. For example, let me draw. Assume it's a 2D wala crystal lattice, no? So many similar exact shape, so many are there, front, back, everywhere. Only the single thing is called a unit cell. All of this is called a crystal lattice. This is called crystal lattice. This is called a single unit cell. A single unit cell. A single unit cell. Okay. So it is the smallest repeating. So many are repeating now. So the smallest repeating unit. Or you also can say it is a 3D group of lattice points. Lattice points that generates the whole lattice on repetition. Okay, this much is only about a unit cell. Can I clear, ma?
Yes, ma'am.
Bravus lattices. Bravus lattices. Okay, so he's a Bravus lattice in 1848. No, he's a French crystallographer. He actually showed from geometrical point of view that there are only 14 ways in which similar points, means any similar point can be arranged only in 14 different ways, that too specifically in a 3D dimension. Okay, so the total number of space lattices belonging to 7 basic crystal systems together is 14. So let us understand each of them. Okay, I'll tell you. Let us understand the types of unit cell. You all are very clear that if you have a cube, so many cubes are like this joined, but the single cube is called the unit cell. You all know that these are the lattice points. Okay, these two are already clear. This is clear. Now, in the types of unit cell, first one is simple unit cell. What is it? It's a simple unit cell. What is this? Something is called as a
Simple unit cell.
Yes, dear.
Nothing.
They called a simple unit cell when you have when the lattice points are only at the corners. When the lattice points are only at the corners, you call it as a simple unit cell, or you can call it as a primitive unit cell, or you can call it as a basic unit cell. Okay, simple, primitive, basic means what? If you have them only in the corners, as I have drawn, these are only the corners. What are the corners? So this one is the corner, this one is the corner, this is the corner, corner, corner. So this is called a simple unit cell that we just have discussed. Let me talk about something called face-centered cubic lattice, which is called as face-centered cubic lattice. FCC is called face-centered cubic lattice. So what happens here? So face-centered cubic lattice, what happened now? Here, the lattice points are at the center of each face of the cube or of the unit cell, as well as at the corners. Understand that the same unit cell that I have drawn as simple will also be included, that is corners have to be there. And what are the faces now? Imagine you have a cube, okay? This is a face, this is a face, this is a face, the bottom is the face, the front is the face, the back is the face. Just imagine, take a dice if you have, or take a watch box, anything which is square, take it. Look at the faces, top one, bottom one, left one, right one, front one, back one. That means how many lattice points are there now? Actually, there are 1, 2, 3, 4, 5, 6, 8 corners here. Okay. You have 6 faces plus 8 corner. All these lattice points are involved under face center. Can I clear the screen? Shall I wait for a minute? Shall I wait? I'll wait for a minute because I just copied. Let me know if I should wait or go ahead. Is it a difficult question? Body-centered cubic lattice. I want all of you to be a bit active, ma'am, because it's a new chapter now. Body-centered cubic lattice. What is this? In this, what happens? the lattice points are at the center of the body as well as corners. You anyways know what are corners. This is the unit cell. You have the lattice points. And what is the center of it? You can see clearly that there is only one center.
Ma'am, you're on mute.
So yeah, so there's one center. For anything, there's only one center now. How many centers will a cube have? In body center. One only or two? One only? Normally, no, normal question. In body centered cubic lattice. You only have one, okay? So you have corners and you will have only one center. So that means what, ma? 7, 8 corners and one body center. One B is one body center. Face centered, I said already 6 faces and things, na? So these are the 3 types of unit cells we just discussed. Okay. Next. Can I clear? So these are the 3 types of unit cells, ma. Good. So these are 3 types of unit cells. But as I said, there are 14 types. 7 types of arrangements are possible. Let me tell you what. If at all, the crystals will be in different shape, right? Okay. These are the axial distances. These are the angles between them. I'll show you. The possible types of unit cells. Oh, sorry, I forgot to tell about the end center. So three types we discussed. We also have another type of unit cell called end-centered unit cell. End-centered unit cell. What is this? This is something which is actually possible for specific things like orthorhombic and monoclinic. I'll show you what each of them are, don't worry. Monoclinic crystal types. So what happens here now in the end center? There are 3 lattice points. 3 lattice points in the face centers of only one set of opposite faces. In addition to, everywhere if you see, in addition to the lattice points at the corners of the unit cell. In BCC, HCC, everywhere we have definitely included the corners. Right? These are the 4 types. So if you have a crystal lattice on the XY axis, and if you have, for example, a cube formed like this, okay, so what will happen now? This is your y-axis, x-axis, z-axis. This will be your angle beta. This one will be your angle alpha. Okay. And this will be your angle gamma. You'll understand why I wrote. For angles, these are the actual angles. Gamma. Beta, alpha, and gamma. Yeah, anyways, I have drawn now. So can I clear now? If you're all done.
Just a minute.
Okay.
No.
Good. So let me show you the table. You will have crystal class, axial distances, angles, possible type of unit cells, and the examples of this, whatever we are doing. So in the crystal class, basically in a cube, the axial distances will be equal, and also the angles will be equal. The types which are possible will be primitive, that is the basic type. Then you have body centered and also face centered. Copper metal, potassium chloride, sodium chloride, zinc blend, which is a ore, and diamond, all of them fall under this crystal class. Those are tetragonal. I'll show you an image of these. Your alpha, beta, gamma is 90. You have primitive. You have body centered. Tin oxide, titanium oxide fall under this. Orthorhombic. Again, it's primitive, body centered, face centered. I also said it is end centered for orthorhombic in specific. We have the example of rhombic sulfur and potassium nitrate. I can also show you pictures first, but then if you write down, then show you pictures, you might relate better. Hexagonal. Hexagonal. Your alpha and beta is 90. Your gamma is 120. Only primitive is possible. It's graphite, zinc oxide, magnesium metal. Magnesium metal. Please copy. I think I can slowly clear the first part. Can I? I'm sure. So next you have.
Yes, ma'am.
Okay. I'm also clearing the second one, assuming you have copied. Trigonal by rhombohedral. We have only two more, okay? Monoclinic. So the next one also I'm clearing, which is the last, which we have to, is the triclinic. A is not equal to B, not equal to C. Alpha not equal to beta, not equal to gamma, not equal to 90. This is primitive potassium dichromate and copper sulfate. Actually, the all structures I'll not be able to, draw it. I can show who is entering the class. Yeah. Let me know if you have done copying yet. Can I clear the screen, ma, all of you?
Ma'am.
Okay. So after this, I'll actually show you how all of these look like, because I cannot draw. Maybe you can just relate, okay? Later, let us actually, we understood terms and we have to start calculating the number of particles per unit cell and all. We have so much fun. It's a lot of calculations. Okay. So I'm ending the session for now. I will continue in the next class by showing you the pictures. I'll always remember that. Thank you. Sorry to end 5 minutes before. I have some work, so need to go. Thank you all. Good night.